So in this problem, we're going to be looking at a mass balance of an incompressible fluid, and we're asked essentially to find the velocity. Sorry, the oh yeah, that's right, the velocity at three different sections within this flow. Um, but as always, we're going to start first with our assumptions, and so start writing them out. And we're going to assume first of all that we have incompressible. Second, steady state. Right, again, that means d dt 0. Um, 3, we're given that it's air at 20 degrees C, which also means 4, we're assuming isothermal. And we'll add to that list as needed as we go through the problem. But essentially, because we have steady state flow that's incompressible, we're also going to assume that we have one-dimensional inlets and outlets. And so in this case, we're going to end up with a very simple form of mass balance that essentially we're going to be applying over and over and over again in this problem. And that's essentially that our flux through the system is constant, equal to V times A. So essentially at each section, we're going to have to figure out this flow rate. So essentially we're going to figure out the flow rate through the whole system, and then we're going to assume that the flux equal to V times A is conserved throughout the system. That's a consequence of this incompressible or constant um, density assumption. The only tricky part here is going to be dealing with the suction out of um, the suction holes that we say. We said in this problem there are 1,200 holes that are 5 millimeters diameter, each per square meter of wall area. So 1,200 holes per square meter of wall area. So we're going to have to deal with that, and that's going to be an additional flux that's moving out of this control volume that we have to keep track of. Okay, so and the way we're suggesting to start this problem is actually by dealing with that first of all. So let's look at um, first of all the um, control volume that considers the flow from V1 to V2. This is going to be section 1, this is going to be section 2, and then up here we have this section S for suction. And we have a flow rate that's going in, a flow rate that's going out, and some flow rate here. Right, so we're going to have Q1, QS, and Q2. And our incompressible steady state 1D inlet outlet mass flux is basically just going to say that the sum of the fluxes in equals the sum of the fluxes out. So in this case, we're going to say that Q1 is equal to QS plus Q2. And we know in this case that Q1 is equal to V1 times A1. V1 is given as 35 meters per second. And we know the diameter at this section 1 is going to be 0.8 meters. And so we're going to have pi 4 times 0.8 meters squared. And so therefore, plug this in, solve for this as Q1 is equal to 35 times pi over 4 times 0.8 squared. So we're going to get this is equal to 17.6 meters cubed per second. So that gives us one of the flow rates that we need to know in this problem. The other major flow rate that we need to know in this problem is QS. In this case, we are given that we have 1,200 holes of 5 millimeter diameter per square meter of wall area. In this case, we can figure out the test section wall area. So the area, the side area of that test section. So we know that the length is 4 meters, and the diameter is 0.8 meters. And so this area of the section is going to be pi times 0.8 meters times 4 meters. And so that's 10.05 meters squared. So that's the area over which we have this, all of these holes that are providing uniform suction. So the number of holes is going to be 1,200 holes per meter squared times 10.05 meters squared. And that's going to be 12,064. So we have 12,064 holes providing uniform suction out. And now we're also given that those holes are each 5 millimeter in diameter. And the suction velocity through each hole is 8 meters per second. That's a relatively high suction velocity through those holes. And so we're going to get that our flux that's leaving out through this control volume is going to be QS is equal to 1264, right, the number of holes, times now the flow rate per hole. Flow rate per hole is going to be velocity times area. So it's going to be 8 meters per second times pi over 4 times 0.005 meters squared, and that's 1.895 meters cubed per second. Okay, so now we have essentially all the things that we know to start the problem, right? So we know the Q1, we know the Q suction. We could go ahead right away now and solve part B, but we'll start with this part A first. So for part A, we want to know the velocity V0 at that inlet. So let's see. So we know that if we look at this test section over the first piece here, there's no suction flow. So the only inlet to this control volume, this first control volume for part A, is going to be V0 times A0. And that's going to be equal to the flux at section 1, right? It's going to be equal to Q1, which is also equal to V1 times A1, right? We've already found this. It's equal to 17.6 meters cubed per second. And we know the diameter of this section 1. And so with this diameter, we can figure out the area. And so to find V0, we're going to say V0 is equal to 17.6 meters cubed per second. And that's going to be divided by A0, which is going to be pi 4 times that diameter, which is 2.5 meters. squared. Put all that together, we should get that V0 is going to be 3.58 meters per second. Okay, let's just check significant digits here. We're giving everything to, at most, 2 significant digits. We'll probably say this is about 3.6 meters per second would probably be sufficient precision for that answer. Okay, so next we're asked to find, let's see, part B, we're asked to find V2, right? Makes sense. So now for V2, right, this is where we have to consider our control volume with inlets Q1 and outlet QS and Q2. And so here we're going to have that Q1, right, our inlet flux is equal to QS plus Q2. In this case, we know that Q1 is 17.6 meters cubed per second is equal to 1.895 meters cubed per second plus V2 times A2, which is just going to be pi 4 times 0.8 meters squared. If we plug all this in, we're going to get that V2 is going to be equal to 31.2 meters per second, which 31 is sufficient significant digits for this problem. Okay, so moving ahead, the last part here is to find VF. If we scroll up, we can see to find VF, now we're going to draw a control volume, something like this. This will be our control volume for C. In this case, we're going to have just one inlet, which is V2, and just one outlet, which is VF. And so we're going to say that the flow rate in is equal to the flow rate out, or V2 times A2 is equal to VF times AF. We know the diameter at the outlet, we know the flow rate and velocity here are at section 2. And so we can more or less directly find the velocity again at the outlet. And note here that in this problem, we have this wind turbine that's sitting in the center of this control volume, and that would certainly affect momentum in this control volume. But in this case, we're not asked to talk anything about the momentum. In fact, one of the consequences of this is that it would probably violate our 1D inlet and outlet assumption. But maybe that's a question for another time. In any case, what we're going to be looking for is VF with this assumption of 1D inlets and outlets. So let's go ahead for part C. So here we're going to have, as I said, Q2, that's our inlet, is equal to our outlet, QF. We know, here I'm going to use just a little shortcut here, we know that Q2 is equal to Q1 minus QS. And so I'm just going to write that out, 17.6 meters cubed per second minus 1.895 meters cubed per second. Just noting here that if we put these two together, this is Q2, and this is going to be equal to our VF times, again, pi 4 times the diameter, which I believe is 2.2 meters squared. And again, if we put this all together, then we're going to get our final answer. The textbook lists this as 4.13 meters per second. Two significant digits are fine, so we're going to say VF is equal to 4.1 meters per second. Okay, so that was an example problem on mass balance. Really, the main thing to solve this kind of problem here is to keep track of your inlets and outlets across each section. And you saw here we had 3 distinct sections, one for section A, one for section B, and one for section C. We just trace the flow, keeping track of our inlets and outlets as we went. It'd be easy to get caught up on this problem, on what's going on with this uniform suction flow, but we saw that really just mainly affects, or it's mainly a complication when we're considering this control volume that includes that piece